On the screen is a dipeptide, in which the amino acid on the left is a leucine, and on the right is a tryptophan. As you know, peptides and proteins have a backbone. With a different sequence of amino acids chained by the backbone, it forms a different peptide or protein. There are 20 common amino acids. Each of them is with a different residue. The residue for leucine is like this, and the residue for tryptophan is like that. The International Union of Pure and Applied Chemistry (IUPAC) has a recommended trivial name and symbol for each of the amino acids, which is the naming convention we have been using. For example, this is H-alpha, this is H-beta, etc. And, correspondingly, the carbons are C-alpha, C-beta, C-gamma, C-delta-1, and C-delta-2, respectively. Similarly, for the tryptophan, we got C-alpha here, H-alpha here, beta here, etc. Also, due to the difficulty in typing, the Greek characters are denoted with Latin characters in the publications, e.g., A for alpha, B for beta, G for gamma, D for delta, E for epsilon, H for eta, Z for zeta, etc. And then we name each residue with a sequence number 1, 2, 3, 4, etc. Hence, the leucine here is L1, where L is for leucine, and the tryptophan is W2, where W is for tryptophan. In NMR spectroscopy, we also unambiguously name the nuclei of a residue with its sequence symbol followed by a hyphen. For example, L1HA means it is the HA of leucine. W2H1 means it is the H1 of tryptophan 2, etc. Remembering this conventional nomenclature is important for us to understand biomolecular NMR spectroscopy. For the Chem 374 lectures, we have been using this typical molecule to explain the application in biomolecular NMR spectroscopy. Because the spectra contain almost all typical knowledge that we may come across for the NMR assignments. This is a proton spectrum for the peptide measured in 99.9% D2O. Here, the water is referenced to 4.8 ppm. There is a formula to calculate water chemical shift in D2O at different temperatures. But it is not important to be precise as long as the experimental conditions and the reference's chemical shift are clearly written in the publication and the assignments can be verified by others. Brucker referenced it to 4.7 ppm, which is also acceptable. If you measure the NMR in 90% water and 10% D2O, you will see a huge water peak that overlaps with peaks around it, which, however, can be suppressed experimentally, as can be seen in the next slide. Let us have a look at the water again. Now, it disappears. This is called water suppression, and it is important. There are a number of NMR techniques for water or solvent suppression, for which there are a number of experimental parameters that can be changed to optimize the suppression. With this peptide, however, we are just lucky not to have any peaks near the water's chemical shift, otherwise, they will also be suppressed or affected. Besides, the water in 99.9% D2O is just a tiny bit, and easy to be suppressed. Later in the tutorial, we can show you an example of peptide NMR spectra in 90% water and 10% D2O. With this slide, we will talk about the observation of amide proton signals. Fact number 1: NH signals can be observed in 90% water plus 10% D2O. So, this NH can be observed, and this can be observed. And it is important to observe them in protein assignments. Fact number 2: in D2O, however, NHs cannot be observed due to rapid chemical exchange between the NHs and the D+ in the solvent. Because D2O in solution self-ionizes to be D+ and OD-, where the D+ exchanges rapidly with NHs so that no NHs in the molecules are observed. Fact number 3: terminal NHs cannot be observed because of the fraying effect. What is the fraying effect? When you wear something for a long time, you can see some loose fibers at the edges, which is similar to the fraying effect at the terminal of proteins. It becomes very flexible, and hence the local magnetic field keeps changing. Therefore, the peaks are broadened severely, and there is no observation of terminal NHs. Let us examine the 1D1H spectrum closely. How many protons are distinguishable? Let us have a look. There are 1 + 1 + 3 for the integration of this lot, 1 + 3 for this lot, 2 + 1 for this lot, and finally 6 for the strongest peak on the right. We then work out that there are 18 protons in the molecule, excluding those attached to ends that are not observable in D2O. Let us see if it is true. From the leucine we have 1 + 2 + 1 + 6 = 10, and, from tryptophan, we have 1 + 2 + 5 in the rings. They add up to a total of 10 protons, correct? This slide is about 1D peak numbering. Note that this is different from chemical element labels, or, in the case of peptides and proteins. They are the conventional names as presented here on the molecular structure. While you can easily write down an assignment with a conventional label in a spectrum, as we can see later, reporting it in a list requires either a chemical shift and the assignment, or a number and the assignment. For multiplets or overlapped peaks, working out their chemical shifts often requires additional work. For example, if you numbered the rightmost peak to be number 13 and 14, you can then simply say H13 and H14 are L1, HD1 and L1, HD2. In a list, the numbered peaks and their assignments can be presented simply in 2 columns, as will be shown later. For teaching, assignments, and exams, it is much easier to number them, because numbered peaks can be easily presented in a list. This is particularly true in a sitting exam when time is limited and only answer sheets are collected, which unfortunately means no spectra can be presented in the answer. As an exercise, for Chem 374 assignments, you are required to number the peaks and list them in a table. Similar inspection and numbering can be done for the 1D carbon spectrum, as shown in this slide. There are 17 carbons in the molecule, and 17 carbon peaks observed, which can simply be verified by counting the number of chemical shifts displayed in the spectrum. The peak numbering is trivial. From left to right, we have 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, plus 3, which equals 17. Often, one carbon peak may represent 2 chemically equivalent carbons in a molecule. For example, the 2 orthocarbons in a monosubstituted aromatic ring are always seen as one strong carbon peak, so are the 2 metacarbons. Be aware that all the spectra for your assignments were measured in CDCl3. Therefore, you should expect to see a triplet of the solvent peak at 77, which is not necessarily to be counted or numbered. It is okay to point out that the triplet is the solvent peak in your assignment. In the past, some students added the triplet to the number of peaks in the molecule. Some even counted the triplet as 3 peaks, which was incorrect. Now, what about the HSQC peak numbering? We have learned about HSQC in the previous slide, which shows 1 bond correlations between C and the H attached to it. For your assignments, I strongly recommend you label the HSQC peaks from the bottom up, because numbering them this way can easily align the HSQC peaks with the proton peaks that are numbered with exactly the same number in the previous slide. You can see how an HSQC peak number matches up with the number of its correlated 1D proton peak, as indicated by the green line in the spectrum. Let us continue with the average chemical shift statistic tables for the 2 amino acids of the peptide, where the 1H, 13C, and 15N chemical shifts are colored in black, red, and blue, respectively. The webpage for a complete set of tables for all the 20 common amino acids is given in the slide. The actual chemical shifts depend on the solvent, temperature, as well as a protein or peptide folding structure, but the chemical shifts are still very useful references for protein and peptide assignments. The table on the left is for leucine. Here in the first row, the H is for the backbone NH, and C for the backbone carbonyl carbon. And, in the last row, the N is for the N in the backbone. Remember that Cb is always the one that connects to the backbone of a peptide or protein molecule. For leucine, the HBs, circled in blue, are diastereotopic and hence separated into 2 values. Besides, it also shows us that, in leucine, the chemical shift of Hg, circled in green, is very close to one of the HBs. On the right are typical chemical shifts for a tryptophan. First, I like you to also have a look at the 2 conventional naming systems for tryptophan's ring elements. One is with the Greek alphabets in black, and the other one with numbers in green. For example, H epsilon 3 is H4, H zeta 3 is H5, H eta 2 is H6, H zeta 2 is H7, etc. For simplicity, we are going to name them with numbers in teaching. Again, the HBs, circled in blue, are diastereotopic and separated into 2. Keep an eye on the last 4 chemical shifts for H4 to H7 in the aromatic ring. We can see that H4, circled in red, has the highest value among the 4, which is useful to be used as a starting point for the assignments of the aromatic H's. Also, keep an eye on the HE1 that has the highest chemical shift among all the listed H's. And it is in fact also a chemical shift that is significantly higher than that of all H's of the 20 common amino acids. This is a useful thing to remember because it allows us to quickly identify any tryptophan in the molecule. Now, let us learn how to do the peptide NMR assignments with 2D NMR spectra. On the screen is the COSY spectrum of the peptide. We can start with a known peak that we can easily assign in the 1D proton spectrum, for example, the rightmost peak that shows the integration of 6 protons. So, we assign this to be the peak for the 2 delta H's of leucine 1 and denote it as L1HDs. We know that COSY gives us 2 to 3 bond correlations. So, from delta H's we expect to see gamma H. Is it true? Yes, it is true. If you look at this, there is a cross peak that correlates delta H's and gamma H. By drawing a line from the cross peak to the left, we found that the small peak there is gamma H. And hence we denote it as L1HD: L1HG, where the double colon means correlates with. And, from the gamma H, we should be able to find a cross peak that correlates it with beta H's. Let's try to find it. Indeed, there is a cross peak that adheres closely to the diagonal line here in a pink circle, and hence it is denoted as L1HG: L1HB. So HB is just next to HG. Continue searching to see if there is a cross peak that correlates L1HB with L1HA. And indeed, we found it right here, and denote it as L1HA: L1HB. So, this is the correlation between beta and alpha. The alpha is somewhere here on the left trace, or here on the top trace. And hence this is assigned to the alpha of leucine 1. Assignments for the HA and HBs of tryptophan can be done in a similar way, as shown with the red arrows. For the area between 7 and 8 ppm, we will zoom into it and discuss them on the next slide. Let us have a look at this expansion, which is for our alkene H's. It contains COSY cross peaks that correlate H4, H5, H6, and H7. Keep in mind that there should be no cross peak correlated to H2 because the NH that is 3 bond away cannot be observed in 99.9% D2O. Again, we need to find a place to start. We know that H4 of tryptophan has the highest chemical shift value among those for the H's in the aromatic ring. So we can start with H4, which is the one around 7.74 ppm. We expect to see a cross peak that correlates it with H5, which is this one, and it is denoted as W2H4: W2H5. If we follow the arrows on the spectrum, we can then find the other 2 cross peaks to assign H6 and H7. I will leave this as an exercise for you to complete. There is one more peak that we haven't assigned, which is H2. The integration of the peaks approximately 7.26 ppm in the 1D1H spectrum indicates that there are 2 protons there. And we know that H2 is a singlet, and H6 is a triplet being coupled to H5 and H7. So, H2 must be the tallest peak, approximately 7.25 ppm, where it overlaps with a component of the H6 triplet. One thing I want to talk about is that 2D homonuclear spectrum has an image on the other side of the diagonal. However, the images of cross peaks often look better on one side but not the other, which is due to unequal data points collected for the experiment. The reason is simple. In the T2 dimension, corresponding to F2 in the spectrum, we can easily collect many points in less than 1 second, say 2048 points. But in the T1 dimension, corresponding to F1 in the spectrum, every point comes from a point of a transformed FID. And hence we are restricted to the available experimental time because every FID requires a number of scans for better intensity and signal-to-noise ratio, which then requires plenty of time to complete. For example, the time for a 16-scan 256 FID NOESY is about 4 hours. If you want to have 2048 FIDs, it will need 32 hours.